Hello class, how are you doing? In this short video, we're going to talk about the applications of the double integrals. We're going to use the double integrals to find the moments, strength center of the mass, and also with centroid. And if you remember in calculus 2, we talked about a fulcrum in a seesaw. And we had certain people are sitting on the seesaw. They have different weights. And we try to balance this fulcrum. Then it was the possibility for me to move this fulcrum either closer to the heavier person, because moment, which is one kind of a force, is always mass times distance. Therefore, whatever I want to do, I want to offset the forces on both sides and make it equilibrium. Therefore, what I'm going to do, I want to take the sum of the masses times the distance from the what? The distance from the center of the mass, from the zero, from the zero, where that one is the number line, minus the x bar. X bar is where we're going to put the fulcrum, and we're going to make this one equal to 0. What I'm trying to say right here when I talk about equilibrium, I want to do mi xi to become exactly equal to the sum of mi x bar, and x bar is the center of the mass. And in here I can go from 1 to n. It depends how many people is going to sit on that one. And in here, because the center of the mass, if I solve for x bar, that become mass xi over the sum of the masses. I didn't write the lower index and the upper index. And someone said, why you use mass? Why you didn't force, or why you didn't weight? Because even if I do mgxi and mg, those eventually gonna cancel out. Therefore, instead of the force, I'm gonna write the mass. This formula is very important. Then, this is only for whenever you're talking about a linear. When we talk about plane, and we want to say what is the center of the mass of this plane, if you remember, we drew a rectangles, and we said if you draw the two diagonals, and if this one has a uniform density, the center of the mass would be here. Then moment, I'm sure many of you have played football or have you watched football, then there is an offense in here and there is some defense in here, and then there's a quarterback in here, and then sometimes those offensive linebacker, they took a few steps back, and the only reason they do that because they are not as heavy as the people standing on the middle or on those people that they are on the offense in the front. Sorry. By stepping back, they can increase the moment by multiplying their weight times the distance, and they can increase it, and then they might be able to have enough force to sack the quarterback. Therefore, moment is always mass times distance. Therefore, this is nothing except mass times distance, and is a moment. And if you want to find the x bar right here, what is my x bar? X bar is the distance from the y-axis. Therefore, it is moment about the y over the sum of the masses. And what is the y bar? Y bar is this distance right here, and it is away from the x-axis. Moment about the x-axis over sum of the masses. Then someone said, in calculus 2, we really didn't deal about density when they are variables, but we talk about uniform density. But in here we will talk about it because we know the double integrals. Therefore, in here your x bar is going to be the double integral, because I hope you know mass is a density times area. And if you want to be able to do the moment is mass times distance. Then it depends if this moment is about the y-axis, the distance from the y called x. If it's from the x-axis, the distance from the x is y. Or if it's from the origin, the distance called r. Therefore, we have moment about the y, moment about the x, and we have moment about the pole. But what is the moment? Mass times the distance. But what is mass? Is the density. And what is the area? Is a double integral of a region times dA. Therefore, this is only give you the mass. But when I want to do x bar, I need moment. Moment need a distance. About the x bar is a distance away from the distance. The x bar is moment about the y, and the distance is x over sum of the masses. And mass is nothing except density times the area. The difference between them is, remember, the bottom is a mass, the top is a mass, but the top also is a mass times the distance we call a moment. There is one extra letter in here. If you do moment about the y, if you want to do the y bar is a distance from x. Somebody said, I don't understand that. Remember, whenever you have an order pair 2 and 3, that 2 is a distance away from the y. And could be anywhere. Therefore, you take 1 and 2, 1 and 2. Therefore, any of them, the x value is a 2. But I am looking for one specific point, the one that the y is 3. Then y is a distance from x. Therefore, this is distance from the y, and that's the distance from the x. Do you see when I talk about x value is a distance from the y, and x and y, they are not same. And when you talk about the y is a distance about the x, then this one, the y value, is going to be moment about the x over the sum of all the masses. But what is the moment? Is mass times distance. Your mass is nothing except density times the area. But I need a distance. Y bar is a distance from the exact is a distance. The y bar is a distance from the is a moment about the x, and the distance from the x is the y value. And this one was moment about the y, and the distance is x. And on the bottom is exactly mass, which is region rho xy dA. Okay, let's solve a problem. You know, I'm going to give you that region. This is your region. Y equal to x squared. And in here is y equal to a square root of x. And I'm going to give you that region. But I'm going to say that region does not have a uniform density. In this piece could make of one material. This piece could make of another material. This piece could make of another material. This piece could be made of another material. Therefore, it depends where you are. Wherever you are, your density is going to be different. Therefore, location is important. If I'm assuming this location, at any given point, I'm going to say the density at the location is defined by x times y. Therefore, whatever the x of that point is, and whatever the y, you double it, that becomes your density. And I want to find the center of the mass. What is my x bar? What is my y bar? In order to know it, you need moment about the x, you need moment about the y, and you need mass. Finding mass is very easy. Mass is rho times area. Rho, we already have it, is xy. Area is a region dA. Let's find out which one you want to get fixed, which one you don't. We want to get varies. In here, the point of intersection is 1 and 1. Therefore, I'm going to make my x fixed, and I'm going to go from 0 to 1. My y is not fixed. Therefore, my lower one is x squared, and the top one is the square root of x. And this is x times y, and your area, because I made my y variable, is dy dx. This is my mass. Somebody said, what is your moment about the y? It's the same thing as this, except when you're doing moment about the y, the distance is x. Therefore, I need an extra x in here. Therefore, I'm going to put x, xy, dA, region, and that become exactly equal to 0 to 1, and this one is x squared, the square root of x times x is x squared y, dy dx. Therefore, do you see the difference between them is only one variable? Same thing with this one. Because when I do moment about the x, the distance is a y. Therefore, in this one, is a double integral of a region, and I need mass times, mass is the density times the area. Your density is this, your area is a double integral, and you need moment about the x. The distance is a y value. And that answer is from 0 to 1, x squared to square root of x, xy squared dy dx. And I am done with this problem. Therefore, what is the moment about the x? You're going to integrate this one. Because you do with respect to y, x is constant. That's become x y cubed over 3 from x squared to a square root of x. Let's scratch this and let's take care of this first. This is x to the power of 3/2. Therefore, this is x times x to the power of, that's 1/2 times 3x to the power of 3/2 over 3 minus, when I put x squared in here, it becomes to the power of 6 over a 3. Therefore, what I have in here is x to the power of 5/2 minus x to the power of 7 multiplied by 1/3. I got my inner one. Then I got to do the out one. Therefore, moment about the x is equal to 0 to 1. And remember, let me see, I already took care of that x because I did keep my x right here. Therefore, and I did apply it. Therefore, I have 1/3 x to the power of 5/2 minus x to the power of 7 dx, and that would become 1/3 of x to the power of 7/2 times 2 over 7 minus x to the power of 8 over 8, and that's become, when I put 0, 1. When I put 1, you get 1, and you get 1. When I put 0, you get 0. Therefore, I have 1/3 times 2 over 7 minus 1 over 8. Therefore, moment about the x is, I multiply this one, that's 16. 16 minus a 7, 16 minus a 7 is 9 over 56 times 3. And that 3 becomes 3 over 56. Well, moment about the x is saying, I don't know what my x bar is because I have not done it, but that's only moment about the x. Let's do moment about the y. Moment about the y is the same except x become x squared. Therefore, I'm going to have the inside integral x squared y. X squared y, but I'm going to do it respect to y. That become y squared over 2. That become y squared over 2 from x squared to a square root of x. And that become x minus x to the power of 4, both divided by 2. I got that inner one. Let me make sure I did it right. Okay, don't forget, I did only y. I did not include that x squared right here. Therefore, my moment about the y is equal to, I have an x squared, I have an x minus x to the power of 4, I do have a 1/2 here, I go from 0 to 1 dx. I think I did everything correctly. Then the answer is 1/2. That become x cubed. It become x to the power of 4 over 4. X to the power of, you add the power. That power of 2 plus 4 is 6. It become x to the power of 7 over 7. And is 0 and 1. And that become 1/2 times 1/4 minus 1 over 7. And that's 1/2 times 7 minus 4 is 3 over 28. And that become nothing except 3 over 56. Not bad. It became the same. Okay. Let's talk about the mass. And this is moment about the y, moment about the x. Mass is easier because you don't have that extra variable. You do it respect to y, is y squared over 2 from x squared to a square root of x, and that's nothing except x minus x to the power of 4 over 4. I didn't have, let me see what I did. I did not apply that x yet. Remember, I just did the y, and everything, this one is going to become, let me check, that's x over 2 and x to the power of 4 over 2. Therefore, I have 1/2 x minus x to the power of 4. Therefore, your mass is from 0 to 1. Don't forget, I did not have x in here. I have an x times x minus x to the power of 4 dx. I have 1/2 here, and my mass is to become 1/2 x squared, that become x cubed over 3 minus x to the power of 5, x to the power of 6 over 6, 0 to 1, and that become 1/2 1/3 minus 1/6, and that's become 6 minus 3 is 3 over 18 times 1/2, and that become 1 over, because that's become a 6, 12. That's your mass. Then what is your x bar? Is moment about the y, because x bar is moment about the y over the masses. Moment about the y was 3 over 56 over 1 over 12. Therefore, 3 over 56 times 12 over 1. When I reduce this one by 4, is 14, by 4 is 3. That becomes 9 over 14. 9 over 14 is 2 point something. And I don't think I'm right. It should be between 0 and 1. And I'm going to check where did I do wrong. 9 over 14. 9 over 14 is correct. For a minute I thought it was 9 over 4. And the y bar is moment about the x over the mass, and is equal to 3 over 56 over 1 over 12, and that's also 9 over 14. Therefore, 9 over 14 is a little bit past 1/2, and it's going to be someplace around here that becomes the center of the mass. But you know how to find two things today. Number one, you know what is mass. Mass is rho times the change in area. Therefore, if you want to find your mass, you always have to take your density as a function of x and a y over the region. You got the mass. You know what the x bar and y bar is. Next thing what we're going to do, we're going to talk about kinetic energy. Your kinetic energy is 1/2 mv squared, but this is a linear velocity. What happens if you have an angular velocity? Remember, the arc length is s equal to r times theta. But if I divide, s is arc length, is a distance. If I divided it by t, distance over time is a velocity. Angle over time is an angular velocity. If I go to my kinetic energy and replace the v with r omega squared, you will get that one as 1/2 m r squared omega squared. They call this one moment of inertia, which is I omega squared. What is the moment of inertia? You are here, you want to throw a disket, you rotate, you rotate, you rotate, you rotate, and throw your disket. Therefore, it depends how big of a radius it is. Radius is a big factor, and it depends how heavy you are. Therefore, from today, you have to know your I is mr squared. And what is r? Is the radius of that revolution here. Therefore, you have a moment of inertia. You have respect to x. Respect to x is mr squared. What is m? Is rho times a. Therefore, this becomes the double integral region dA. I took care of my area. I'm going to take care of my density. Density is rho xy. Okay, I got the mass, but I need my distance. If you're doing it respect to x-axis, that distance is called your radius, and that's called y squared. That distance is y squared. And it depends which one you get fixed and not fixed. Therefore, you can change this one to dy dx or dx dy. Or you can do it respect to y, and then respect to y, that's the region. Your mass is a density dA, but when you do it respect to the y, your radius is going to be x. But you need radius x squared, radius squared. That's respect moment of inertia respect to y. But somebody said, what happened if I wanted respect to the origin? Respect to the origin, this is your radius. And that radius, you have to say r squared. And r squared is x squared plus y squared. Therefore, if you want I, they call it polar moment, is going to become r x squared plus y squared, that's your distance, density dA. That's the polar moment. But somebody said, oh, if I find the inertia respect to x and the inertia respect to y, I can add it together, because this one is nothing except I of the x plus I of the y, because that's the sum of two double integrals. Yes, you can do that. Therefore, these are application, and nothing is hard about these, because it still is a double integral. You're just adding more variables. Another thing you need to know in here is the radius of gyration. What is the radius of a gyration? You said I is equal to r m, not r. I equal to m r squared. That r is the radius of a gyration. Our radius can be only positive and is I over m. Therefore, if you need a radius of gyration respect to x or respect to y, that's something you're going to see it in physics. Therefore, these are some of the applications regarding the double integrals. You can find the center of the mass. You can find this center of revolution. You can find the mass. You can find the center of the mass, and many other things. Hopefully, in the next video, we are going to talk about more application. Thank you.